I want to just introduce the Heisenberg uncertainty just very briefly, and then on the very last lecture that I record, that I'm going to call Lecture 7B, we'll finish off this discussion of Heisenberg, as well as a notation we're going to use to make our life easier, to keep ourselves from having to write out all of these numbers. So, as a result of all of this stuff, so consequences of superpositions, expectation values, and so on, okay? It is impossible to specify simultaneously with great precision both the position and momentum, which is really to say the velocity of a particle. Quote Werner Heisenberg himself, okay? So if the position is precisely defined with a large number of superpositions, then all information about the momentum is lost, because any observation of the particle's momentum will be one of the many momentum states used in the superposition. So the way I like to kind of describe what's going on with Heisenberg is if we keep adding more and more and more of these superpositions to get a very precisely defined wave function, we know exactly where the particle is. It's right there. However, we don't know where the particle has been. Think about that for a minute, right? If we know exactly the particle is right there, well, we've added 20 of these momentum states to get to that level, to know that that's where it is with this very tight amount of precision. But because of that, because we've added these 20 plus states, suspect to this large number of averaging, okay, the velocity, in other words, the momentum, so where the particle has been in time, right? We lose tons of accuracy and precision for that case, okay? So the equation for Heisenberg is given by the following. Delta P, so that's the uncertainty in the momentum, and this is not given as final minus initial, rather it's given as an arithmetic uncertainty, okay? So this is the mean square minus the square mean, all square root, which is just a type of uncertainty, like it's a variance, if you will, okay? So Heisenberg says the uncertainty in the momentum multiplied by the uncertainty in the position must be greater than or equal to 1/2 h bar, okay? So for example, if I wanted to know what is the, let me get rid of this thing. If I wanted to know what is the uncertainty in the particle's position right here, well, according to this plot of psi squared, and again, this isn't the same, you know, I'm not getting like a peak from this wave function. And we're going to see that. Sometimes we're going to see wave functions that look like this, that give us this peak, okay? Sometimes we're going to see wave functions that have these exponential decays, all right? So what's the consequence of that? Well, the consequence of this particular wave function, which is actually a realistic one, this is the ground state hydrogen atom. The uncertainty in the position for this wave function is roughly 140 picometers, right? Because it's saying from 0 to 140 picometers, there is finite probability of finding the particle anywhere along this axis. Whereas the expectation value here says it should be about right there. But even so, there's probability finding the particle up here, and there's also probability finding the particle way down there, okay? So if in the case for hydrogen, all right, so I'll say in the case of, I'm going to write hydrogen 1s, because that's what we have here. We have the hydrogen atom, the 1s electron, okay? This delta x is, I'm just going to say roughly 140 picometers as given by our wave function, okay? where of course now we could use that 79.35 value, right, to calculate that. So that's why I'm just saying it's approximately 140 just by looking at this graph. So now I can calculate what the uncertainty in its momentum is just by simply dividing and doing the algebra. And what's going to happen is because h bar is like 10 to the minus 34, right? And this number is like 10 to the minus 12, we're going to get a very large value in the momentum uncertainty. And if we were to continue to make that delta x smaller and smaller and smaller and smaller, the delta p would have to get bigger and bigger and bigger and bigger. Okay? So let's see here. I'm at 32 minutes, and I think that's a pretty good place to stop. I'm going to pick up with this more on Heisenberg uncertainty in the next video.